so last day we are discussing about switch chart and some of the basic properties of switch chart. Let us go to recapitulation first. So we can represent the reflection coefficient and its relationship with the load in switch chart. And here, this is actually the reflection plane, and along x-axis we represent the real part of gamma, along y-axis the imaginary part of gamma, and we then have two sets of circles, one for the resistance, another one for the reactance. And if you note down on the Smith chart, then all the solutions for passive components, it will be inside magnitude of gamma equal to 1 circle, and where it is crossing gamma r equal to 1 point, so that point corresponds to the resistance and reactance equal to infinite, and similarly at gamma r equal to minus point, resistance and reactance approaches 0. And we have seen last day how to plot these different circles, and basically these are the equations of circles, and the center point and the radius values are given here. Now let us use Smith chart to solve one simple problem. Let's say some transmission line is given with characteristic impedance of 50 ohm, and it is terminated with a load 20 plus J35 ohm. So then you have to calculate Z in seen by the source, the reflection coefficients, and the source and at the source and load ends. So source, it is connected 0.3 lambda away from the load. Now you see here, very first step, if we go back here, then we have to represent the normalized value of load impedance. So load value is given 20 plus J35 ohm, and characteristics impedance is 50 ohm. So divided by 50, then we have normalized ZL, which according to DM Pujar's notation, we are representing by small z capital L. That becomes 0.4 plus J 0.7 ohm. Now let me okay, so you have, I think, the Smith chart, all of you downloaded. Then you find out the circle which corresponds to 0.4. Then you have the resistance circle. Then you go to the reactance circle and find out where it is 0.7. So if we see that, then let me zoom it in. Then ZL corresponds to this point. So we denoted it by 0.4 resistance circle and 0.7 reactance circle. So ZL is given, then we can read out what is the reflection coefficient at load end, because this is the gamma plane. So what will be the magnitude? So you have to just measure from center to this ZL. This distance will give you magnitude of gamma at load end. And what is the reflection phase? You measure it from gamma r axis. Then these values, it comes 0.59, and it is represented in terms of lambda. So in angle it is 140. 0.59 is the magnitude and angle is 140. So next, what we have to do, it is given that now we have to move to generator end, source end, by a distance of 0.3 lambda. So lambda scale is given, and if I go back, you recall that when we go clockwise, it represents towards generator, and for moving towards load, we have to go anti-clockwise. So now we are moving towards generator by 0.3 lambda. So you follow the lambda scale and move by a distance of 0.3 here, and you follow this gamma circle, because we are assuming here lossless line. So magnitude of gamma will not change, only the phase will change. So we follow this circle and move by 0.3 lambda. Then we have the corresponding this value, and you read out what is the value of R at this point, resistance and reactance. So it comes 0.365 and the reactance minus 0.6 minus J0.6. So it becomes capacitive now. Previously it was inductive. So once you have this value, this is actually the normalized value. Then what is actual Zn? Now we have to multiply it by 50. So if we do that, it comes 18.25 minus J 30.55 ohm. And the corresponding reflection coefficient, again you read it, magnitude remains same, only the angle changes. Well, so this is a very simple problem. Now, let's say in the previous case, we considered only resistance and reactance, but in some problem, let's say the conductance and susceptance is given. Then what to do? So particularly for the parallel networks, we call shunt network. So for shunt network, it is easier to handle with conductance and susceptance. So there are two alternatives. One thing is that we can generate a separate Smith chart which will deal with only the susceptance and conductance, or we can use the same Smith chart as before, but we have to move by a distance. Well, so what is the logic behind it? Let me discuss. So if I look at the current and voltage plot for the standing wave ratio, then where we have voltage maxima, at the same point we have current minima. If you go back to standing wave pattern shown here, so this is not sinusoidal, not like maxima minima, it is a standing wave pattern. And why we are calling it as a standing wave? Because maxima minima position is fixed. They are not changing with time. It is like a string problem tied at both ends. So same thing here. So that's why from one peak to next peak, or one minima to another minima, separation is lambda g by 2. It's not a pure sinusoidal. So this minima point corresponds to 0, basically. So from here, what do we see? That where we have voltage maxima, their current is 0. Similarly, where we have current maxima, voltage is 0. So then, if I move by a distance of lambda g by 4 quarter wavelength, then actually the reactance and the resistance, they convert to corresponding susceptance and conductance. Mathematically also we can show it. Very simple. Okay, let me. We start with the basic equation. Okay, so here what we do, we start with the basic equation of Z in equal to Z naught ZL plus Z naught tan theta divided by Z naught plus ZL tan theta. So this is at the load end. Now, so basically we have a transmission line and a load is connected here. Now, what we want to do, we want to calculate a in value at a distance of lambda by 4. So, E corresponds to or theta equal to 90 degrees. So, if I have to put theta equal to 90 degrees, so better we rewrite it by dividing both numerator and denominator by tan theta, then z naught by tan theta ZL. So it is coming, then now I put the value JJ of JJ. So which corresponds to Zn by Z naught. This is equal to, you can write down JJ or J. So you see, if I consider the normalized values, then at a distance of lambda g by 4, we have just opposite thing. So okay, I think you can see my PPT now. So then ZL, it basically becomes YL. So we can use this property and implement it in the conventional Smith chart. Then we'll read the value. Let's say ZL is here. So if I move now 90 by 90 degrees, so if I move by lambda g by 4, then in reflection phase it is changed by 2 times of that. So last year we have seen it. So we have to move here by 180 degree. Yeah, here this expression. So you can see then here, if I move by d, then actually for reflection phase it is changing by twice of that. So you can move by that distance and we can have that value and consider it as the YL value. Or another thing we can do to obtain the conductance Smith chart, admittance Smith chart, then we rotate the whole Smith chart by 180 degree from the same logic. Then these values remain same. We don't have to think about like that. So in fact, there are some Smith charts available where both the impedance and admittance are plotted, and it looks something like this. So sometimes it becomes really difficult to read the values because now you have two different sets of values. One corresponds to the admittance and another one corresponds to the impedance. So in our class, what we'll be doing, we'll be using the same Smith chart, and if the admittance is given, then we convert it to impedance by moving that distance. Okay, so here this part ends, and after this we are going to start guiding structures in general. So till this point, do you have any question? You can type here or you can ask me directly. Well, in that case, we'll start part 2. Here we are going to learn about different guiding structures. Now, here I am showing some of the popular guiding structures. One is rectangular waveguide, micro, and then in PCB technology, microstrip line and round back CPW line, and another category is coaxial cable. So our target is to find out electric field and magnetic field distribution inside the guiding structures and define different modes and their characteristics. So how they behave in time and space. Now, why we need so many different types of guiding structures? Actually, all of these guiding structures, they have their own advantages and disadvantages. So later we'll discuss in detail. So for now, for example, if I consider rectangular waveguide cross-section wise, actually it is the biggest among all the popular guiding structures. Now, even then, it is very popular because of its two properties. One is it will provide you least loss, that alpha part is minimum for rectangular waveguide if you compare with other popular guiding structures. And the second advantage is highest power handling capability. So because of these two advantages, rectangular waveguides are popular for high power radar applications, where sometimes peak power can go up to kilowatt to megawatt range, and we can't use PCB technology or coaxial cable for that. And for the least loss cases, when you go up in frequency scale, particularly to sub-millimeter frequencies or terahertz frequencies, so there again, rectangular waveguide is very popular. So at terahertz frequencies, the cross section of rectangular waveguide, it becomes small. So size is not a problem, but loss becomes an issue. So that's why we'll see later. One reason we know that because of the skin depth, loss increases with frequency, and there are some other reasons we'll discuss later. Well, now coaxial cable. Coaxial cable, it is lossy structure compared to waveguide, but it has one advantage that it is flexible. So we have flexible version and semi-rigid version of coaxial cables. You can turn it, you can twist it. So that's why with almost all the measurement instruments like vector network analyzer, spectrum analyzer, then RF shorts, which we have in our microwave lab. So with all these measurement instruments, you will see then they are connected with coaxial cables because of its disadvantage. Well, and in PCB technology, it simply becomes compact. It's a two-dimensional structure. So for microwave PCB, loss is one important issue. So the PCBs or the substrate material or the dielectric material, what we use at low frequency, let's say at kilohertz or megahertz, we can't use the same thing at microwave frequency. So we have some specified materials available for which dielectric loss is really low, and we use only those materials at microwave or millimeter wave frequencies. So main advantage is its compactness and easy to fabricate. We have PCB prototyping machine in our PCB lab downstairs, ground floor. Well, so what is our target? I said then in general, we have to find out electric field, magnetic field distributions and the mode characteristics inside a guiding structure. Now we can have different guiding structures. So let us consider these two different scenarios. One is two conductor system. It looks like a coaxial cable, but it can be of arbitrary shape. Not necessarily it has to be always circular. The second one, it's a waveguide structure. It's like a pipe, hollow pipe. So again, shape can be arbitrary. Even though in our syllabus, we will cover some regular shape only. Well, then what is the general technique? I'm again following the notations given in DM Kojar's book. And you see, we start from wave equation. So electric field and magnetic field, we can write down in terms of X, Y, and Z values. So in DM Kojar's book, what he did, he divided it into two components. One part he is calling the transverse component. So if the wave propagates in Z direction, then transverse components are X directed component and Y directed component. So the these values he is representing by E vector, which is a function of X, Y, and by E bar. Similarly, for the magnetic field H bar, which is a function of xy, and the component which is propagating in z direction, it is separated and separately written as z cap Ez function of xy, and we have the propagation factor e to the power minus j beta. In addition to this, we have a time dependent component which is represented by e to the power j omega t. So with time also, electric field and magnetic field, it is changing at a given point in space. But since e to the power j omega t, it is common to all of the terms. So from this point onward, we are not writing e to the power j omega t. If you recall the solution, the phase part, it looks like e to the power j, then omega t minus k dot r, or k dot r simplifies to beta z if I consider direction in propagation direction in z direction. So you remember then, from this point onward, we are not considering e to the power j omega t part. Okay. So we will follow the D'Ampoger's notation. Now let us consider two curl equations, curl H and curl E. So curl H, that is equal to J plus del D del T, and we are considering time harmonic fields represented by e to the power j omega t. Then if I put the value and if we consider it is source free, it's just inside the guiding structure, that is source free, then j, that becomes 0, and you put the value, then we have from del d del t, it is j omega epsilon e, where t equal to epsilon e. Similarly, our curl E, it is minus del B del T, B equal to mu H. So time harmonic, we have the e to the power j omega t. Then we have a omega term here, and curl E, it becomes minus j omega mu H vector. Well, this is for source free region. Now we have then 6 components of electric field and 6 components of magnetic field. So we can utilize this equation and we can relate this 6 component of 3 component of magnetic field and 3 component of electric field. So altogether 6 components. Sorry. So we can relate it. How you might have used that determinant form. I'm not repeating here in EM theory. So I cap, J cap, K cap, then del del x, del del y, del del z, then ex, ey, ez. So from that we can expand the left hand side expression, equate it to right hand side expression. So H vector, then in general we can represent it in terms of I cap, J cap, and K cap component. So relate these two terms. So finally then from these two equations we have 6 components. So left hand side, you see, we are actually equating the I cap component, J cap, and K cap component. Similarly here for the electric field. So you see here we are simply neglecting e to the power j omega t part because it is common to all expressions. Anyway, so we can rearrange these 6 components and to have these 4. So what is our target? That we want to represent all other field components in terms of the Z components. Then if you try it in your room, then Ex, it is written by minus j by k square beta del del x of Ez plus omega mu del del y of Hz and so on. So where kc square, it is equal to k square minus beta square. This represents the dispersion graph. And what is k and what is beta? They are the phase constant. So basically change of phase per unit length, and beta, that is for the guide and K, that is for free space, unbounded space. Better to say. For free space, it will be K naught. Well, so we see then Kc, we have a cutoff wave number, and wave propagation is possible in general when the frequency is sufficiently high so that K is more than Kc. So we have a cutoff wave number K, which is given by 2 pi by lambda. We can also represent it in terms of frequency, noting down the relationship that Vp equal to lambda into F. So we can also represent it in terms of frequency. So from this point onward, we can use these expressions to obtain electric field and magnetic field distributions inside a guiding structure. Well, so some of the part I will skip this time. Now let us consider what are the possible scenarios. There are three possible scenarios. The first one we call transverse electromagnetic wave or TEM wave case. Then we have transverse electric or TE case, and we have transverse magnetic or TM case. So for TEM, let us start with TEM case. For TEM case, it is transverse with respect to direction of propagation. So that means in the direction of propagation, the electric and magnetic field values are zero by definition. That is Ez and Hz, it should be zero. So if it is zero, so we can't directly use that relationship. Later I'm coming to this point when we'll be discussing about one example. So in general, in for most of the cases, we start with the Helmholtz wave equation, so which you learned in your EM theory. Okay, and after that, we will be using the boundary conditions to find out the electric and magnetic field relationship. So for TEM case, you see in this expression we represented Ex, Ey, Hx, and Hy in terms of Ez and Hz. So for TE and TM case, we can follow this. But for TEM, we have an issue because Ez, Hz is zero. So for TEM case, then what we do? We start with Laplace's equation. Then there will be some unknown constant. Apply the boundary conditions to find out these unknown constants, and then we can represent the electric and magnetic field in space. For TEM case, we will see soon that we can define voltage and current on a given cross-sectional plane. So since V and I we can determine, then we can also write down the characteristics impedances. Now for TE and TM case, actually it started with Helmholtz wave equation, and we are going to use these four equations. Well, again the same thing, but we'll start here from Helmholtz wave equation. You see the similar thing here. We are using these expressions, and then depending on the guiding structure, we'll apply the boundary conditions. It will be more clear when we'll discuss one example. Now for TM case, for transverse magnetic, then by definition in the direction of propagation, magnetic field is zero. Well, again we follow the same relation here, but here you apply Hz equal to 0 and Ez not equal to 0. You see the same four equations. It simplifies to now these four equations. Ex equal to minus j beta by kc square del del x of Ez and so on. Well, for TE and TM case, we'll see that we have finite Kc. Let us take one example better. It is easier to understand with an example. We have two parallel plates, metal plates. They are separated by a distance d, and the width of the metal plate is given as W. Inside, we may have dielectric material or we may not have. In general, let us consider the medium is represented by mu and epsilon. It is a dielectric medium. So sigma equal to 0. So we have metal at y equal to 0 and at y equal to t. Other than that, we have dielectric medium. Now, first we consider TEM scenario. That means Ez equal to 0 and Hz is also equal to 0. So what I said for TEM case, we can't use Helmholtz wave equation because both Ez and Hz becoming 0. So we start with Laplace's equation, which is del square phi equal to 0. So del square phi equal to 0 inside this guiding structure. And now what are the boundary conditions? If I consider electric potential, let us consider a reference plane. Let's say reference plane is defined by the bottom plate. So then, since it is the reference plane, you use the concept of ground, which we discussed in last week. So since we are representing it as the ground plane, then phi on this plane, that is equal to 0. And at y equal to t, phi is represented by some potential V naught. So difference is actually 0 to V naught, that means V naught. So then the boundary conditions, you can read that as phi x 0, it is 0. And phi at x t, it is V naught. Well, so what can be the solution of this Laplace equation? Now we have to use little mathematics. So since looking at the structure, let us do some simplified analysis. Actually, at x equal to w and at x equal to 0, we have open circuit plane. So for now, we are not using it. So if I don't impose this boundary condition in x direction, so we are expecting actually no variation of field along x. It is somewhat like semi-infinite plane. So if that is the scenario, then now little mathematics. So from Laplace's equation, we can predict that phi, which is a function of x and y, it can be represented in like a plus by, linear form. Now apply the boundary condition. So what are the boundary conditions? Phi equal to 0 at y equal to 0 and phi equal to V naught at y equal to t. So if I put phi equal to 0 at y equal to 0, a becomes 0. And at y equal to t, phi equal to V naught. So then v is equal to V naught by t. So then in general, I, which is a function of x, y, we can represent it by V naught by t into y. So we have variation only along y. Then how to calculate electric field from electric potential? It is minus grad phi. So electric field, according to D'Ambrosier's notation, if you recall, then we have the transverse component plus z-directed component. I am using its original definition. Then the z-directed component is 0 here by definition because it is a TEM wave. Then what about this EXY? EXY, let us calculate. So we take a minus gradient of phi, then we have only y dependent component. So it comes then minus del y. If I take, it is V naught by t. So minus y cap V naught by t. Electric field, according to our chosen boundary conditions, then electric field, it is in negative y direction. And total electric field, it is then represented by minus y cap E naught by t to the power minus j k z. So we are representing that space variation. It is actually representing the phase part, j k z. So in case if we consider lossless scenario, then it simplifies to j beta z. I'll have alpha equal to 0. Well, how to find out magnetic field then? We have now expression for the electric field for TEM case. Now for magnetic field, if you recall, 1 by eta z cap cross E, that provides the magnetic field. So put the value of electric field here. So magnitude becomes V naught by eta t, and phase e to the power minus j k z. Now what about the direction? It is z cap cross y cap with a negative sign. Z cap cross y cap with a negative sign. So it becomes basically x directed. So we have solved it using this simplified approach. And magnetic field we have seen between these two plates, it is in x direction, and electric field it is in negative y direction, right? Now eta, you know, this is equal to square root of mu by epsilon. So we have now the expression for electric field and magnetic field. We can calculate then voltage difference between two plates. So how we do that? Basic definition is minus integration of E dot dl. So here we use the same relationship, minus E dot dl. So it is then V equal to minus, we are doing it y equal to 0 to y equal to t between these two plates. So EUy dy, put the value here. We have already the expression for electric field. So it is then become V naught e to the power minus j k z. So it looks like a transmission line, right? For a transmission line, if you recall lossless scenario, then voltage magnitude remains same, but its phase changes in the propagation direction. Now, what about current? So current, we can we have metal plates, right? At y equal to 0 and y equal to t, we have two metal plates. So on the metal surface, we have some conduction current, which we can represent by the surface density of current, let's say Js. Then if Js is the surface density of current, so current is flowing in which direction? Z is the propagation direction. So current will flow in the Z direction. So how to find out? So we take Js dot Z cap and integrate it over its width. So x equal to 0 to w. Js dot Z cap dx. Now, how to calculate this surface current Js? We are going to use that boundary condition relationship, if you recall. So induced current, that is equal to N cross H. Now here N, it is negative y direction. So it is minus y cap cross H. That represents the induced current Js. So you put it. Now already we calculated what is the value of H here. It is x cap V naught by eta t, and we have the phase variation. So put it here, integrate it x equal to 0 over x equal to 0 to w. Then we have w V naught divided by eta d and the phase part. So we can define current and voltage at any given z on any cross-sectional plane. So since we can calculate voltage and current, then we can define the characteristic impedance. So it is voltage by current simply. So voltage we calculated here, E naught e to the power minus j k z, and current it is this. So you divide it, then we have eta d by w. What about the phase velocity? Basic relationship omega by beta, and that is equal to 1 by square root of mu epsilon. So you see, then if I look at the characteristic impedance, it depends on the dimension of this parallel plate, d separation, w with also what is the material we are using inside. Eta depends on it. So it also depends on then mu and epsilon. Now, if you are asked to design a parallel plate waveguide with a characteristics impedance of 50 ohm, let's say dielectric material is given, then accordingly we can choose our D and W to have 50 ohm characteristics impedance. Now, when we buy substrate materials from market, this thickness T, it is actually predefined. You can't tune it. So some standard values are possible. So now let's say you bought the material, then you know your epsilon R thickness is defined. So you choose your W value to obtain the characteristics impedance. Okay, and you see the direction of electric and magnetic field, how it looks inside the parallel guiding structure. So electric field, it is in Y direction, and magnetic field, it is in X direction. So we actually used simplified analysis. So we can only predict inside the guiding structure. What happens just after outside, actually for that we have to go for full wave simulation. And in fact, you can define your W, epsilon, mu and D in the full wave simulation you are doing in lab, and you can calculate the characteristics impedance and you can find out electric field and magnetic field distributions. So because of this open circuit at x equal to 0 and at x equal to W, we have actually two boundaries which we did not consider in this simplified analysis. So if I use that, then we'll see that just on the edge, and after that this field component, it bends as I have seen here, and magnetic field, it forms a loop. From here it goes up, then comes back here. So magnetic field, it forms a loop surrounding a plate, and this is in TEM mode. We don't have any component of HZ or EZ. Well, next thing is TEM mode and then TE mode. So for TM and TE mode, we'll be starting from Helmholtz wave equation, and if I go back, already we have simplified it. You see, from Helmholtz wave equation, we can represent electric field and magnetic field in terms of Ez and Hz, and further it simplifies if I put Hz equal to 0. Similarly for the TE case also. For TE case, if I put Ez equal to 0, it simplifies to this. So we'll be using these two sets of equation, this one and this one, to solve for Ex, Ey, Hx, Hy. So I don't think I can cover it today. So tomorrow I'll start with this. So for now, let me take some question. Susceptance, conductance given, then lambda g by 4, yes, but in Smith chart you have to go by 180 degree. Now for reflection phase, it is double of your distance. You can have, actually we'll be using this same approach when we'll solve transmission line problem later by using Smith chart, most probably after 1 or 2 weeks. We have one more question. Voltage reflection coefficient. Yes, so it can be any value, not necessarily less than 1. Yes, you are right. Last day we discussed. If it is a passive component, then magnitude is always less than 1. We are considering magnitude. or maximum possible value is 1. ZL, that is a complex quantity. To put the value, since it's a minus, then we have always equal or less than 1. But if it is an active component, in that case, it can be more than 1. Any other question? No, switch chart. Okay, Danai, another question. So in the switch chart, by definition, how we used that gamma equal to 1 circle. So all the solutions for passive components, it will be within that. And I'm not sure how much we'll be covering for the oscillators. We'll see later if time permits that when we design oscillator with active component, so in that case actually it comes outside the switch chart, because in that case your gamma can be more than 1, as I said. Okay, so that scenario is complicated, so that's why usually we don't cover in UG class. Any other question? Okay, test, I'm coming to this point. We have to discuss some point. So now regarding this technical part, let us complete the discussions. Then we have to discuss about the test. Okay, I assume that you already finished. Yes. So now I'm coming to test and other thing. First, you see, I missed one point. If you look at your central timetable, and I think it was also discussed with you by I with when you went to orientation. So since total semester duration is now squeezed, so what is suggested that for 4 credit course we can use another 1.5 hours from Saturday. Since we are following C4, the time slot it is given. If you go through last line, let me zoom in. So you see Saturday 10:30 to 12 o'clock. It is for the C4 slot. So what we are planning that in 1 week we will be conducting test, and in the following week we will be doing some problems we will be solving. Okay, that's how we'll be proceeding. So Saturday class we have to cover, otherwise we can't complete our syllabus. So last time we announced that test will be on this Wednesday. Now next plan is that we'll be changing this to Saturday, this Saturday only, starting from 10:30, and this Wednesday we'll be arranging one mock test. Okay, so I'll take first 1.5 hour of class, and after that you will be asked to go through this test, which will be through MS Teams only. You will get one invitation soon, and then in Wednesday class slot 9:30 to 10 o'clock you go through this mock test. Okay, and the syllabus it is till today, whatever we learned. If you have any confusion, please let me know.